The third class of reactions that we'll look at in section 4.2 are what are known as oxidation-reduction reactions. Oxidation-reduction reactions are also sometimes known as redox reactions. In redox reactions, what occurs is that electrons are transferred from one reactant to another. The reactant that loses electrons is said to undergo oxidation, and the reactant that gains electrons is said to undergo reduction. You can conveniently remember this using the mnemonic oil rig, which stands for oxidation is loss and reduction is gain. So a typical example of a redox reaction is when a metal, which likes to lose electrons, reacts with a non-metal, which likes to gain electrons. So if we consider the combustion of magnesium in oxygen, what we would expect to happen is electrons would move from the magnesium to the oxygen. Now this is going to result in the formation of a cation from the magnesium and an anion from the oxygen, and they'll be attracted to one another and form an ionic compound. We can break this oxidation reduction reaction into two what we call half equations, or sometimes people call them half reactions, to see more clearly what's happening. The magnesium loses 2 electrons, forming the magnesium 2+ ion. And we know that magnesium likes to do this because magnesium is a metal, so it likes to lose electrons. And magnesium in particular is a metal that's in group 2A, the alkaline earth metals, and so it likes to form a 2+ ion to have an electron configuration like its nearest noble gas. The oxygen gains 2 electrons, and that results in the formation of the oxide anion. And we know that oxygen likes to form an anion because it's a nonmetal, and because oxygen is in group 6A, we know that it likes to form a 2- anion, giving an electron configuration like its nearest noble gas. So we say that the magnesium underwent oxidation because it lost electrons, and the oxygen underwent reduction because it gained electrons. Another way of characterizing what happened is we can say that magnesium gave 2 electrons to the oxygen, causing the oxygen to be reduced. So the reactant that undergoes oxidation, because it causes the other reactant to get oxidized, is labeled as being the reducing agent. Now the oxygen takes 2 electrons from the magnesium, causing the magnesium to be oxidized. So the oxygen can be labeled as the oxidizing agent because it causes the magnesium to become oxidized. And that's a pattern that we'll see in every case. The reactant that is undergoing oxidation is the reducing agent because it provides the electrons that result in the other reactant being reduced, and the reactant that undergoes reduction is the oxidizing agent because it takes electrons from the other reactant, causing it to become oxidized. And that can be a little bit confusing at first, and we'll mention it a couple of times just to make sure that the point is driven home. So one of the more interesting redox reactions is the thermite reaction. And in the thermite reaction, what happens is solid aluminum reacts with solid iron 3 oxide to produce a lot of heat, liquid iron at around about 3000 degrees Celsius, and solid aluminum oxide. And because this reaction produces liquid iron, it's often used for welding. So one can build a porcelain mold, put the solid reactants in there, and initiate the reaction, and it will generate liquid iron that will weld pieces of metal together. So there are a lot of videos of this. You can look it up. I'll just show you a quick one now. This is 6 pounds of thermite, and hopefully at the end of this what you'll see is a big pile of liquid iron. So there it goes, the glowing orange color characteristic of liquid iron. And if you're observant, you'll see the liquid iron pooling at the bottom underneath the brick there. And I think we get a shot of this in a moment. But there we go, lots of liquid iron pouring down there. And there it is, you can see the blob of liquid iron at the bottom. Okay, cool. Okay, so it's important to realize that oxidation and reduction occur simultaneously, and one cannot occur without the other occurring as well. So that's the reason that we say that the reactant that is oxidized is the reducing agent, because it causes the other reactant to get reduced. And then the reactant that is reduced, that gains electrons, is called the oxidizing agent, as it causes the other reagent to be oxidized. So one can't occur without the other. It is a transfer of electrons from the thing that is being oxidized to the thing that is being reduced. So in the example of a metal reacting with a nonmetal, it's pretty obvious that the electrons are going to move from the metal to the nonmetal, because metals love to lose electrons and form cations, and nonmetals love to gain electrons and form anions. However, if we have a more complicated scenario, say we have a couple of molecules coming together to react, it becomes less obvious what way the electrons are going, or if electrons are being transferred at all. So to help us understand how electrons are moving around in chemical reactions, a system called oxidation numbers has been developed. And what we do when we're using this system is we give every atom or ion in a molecule or polyatomic ion an oxidation number. And then we observe what happens to those oxidation numbers as we move from the reactants to the products. So our first challenge is to learn the rules that are going to allow us to determine the oxidation number of an atom in either a molecule or a polyatomic ion. So these are the rules that are listed out in your book. There's 4 rules, but really there's more than that, because the third rule has 3 bits to it. You can find other lists of these rules that are worded slightly different if this one doesn't kind of agree with you. But let's just look at the rules. It says the oxidation number of an atom in an elemental substance is 0. So one of the first things that I would do is look for any elements in your reaction and see if you can assign them an oxidation number of 0. So in our previous example that I was showing, you can see that we could go through and give these 4 oxygen atoms here the oxidation number of 0. And then it says the oxidation number of a monatomic ion is equal to the ion's charge. So that's pretty easy. You just look for an ion, and if you see any ions there, then the oxidation number is just equal to the charge. And often we can get the charge from the periodic table. Now we have a series of rules that relate to the oxidation numbers for common nonmetals. Hydrogen, when it's in compounds combined with nonmetals, has an oxidation number of +1, but when it's in compounds combined with metals, it has an oxidation number of -1. So in this example, I can go ahead and give hydrogen an oxidation number of +1 in each case, because in both of the cases there, it is combined with a non-metal. The next rule has some sort of exceptions to it, and we'll talk about those in a little bit of detail. It says oxygen in most compounds is -2. In peroxides, it's -1. So peroxides are compounds where we have 2 oxygen atoms connected to one another in a series. The only one that you really need to be aware of is hydrogen peroxide. Okay, very rarely -1/2, so-called superoxides. We're not going to be using that. It's so rare that it's irrelevant at this level in your chemistry education. And then positive values when combined with fluorine. and we do need to keep that in mind. So let's have a look at our equation here and see if we can see any oxygen in compounds. There's two cases, the CO2 and the water, and neither of them are hydrogen peroxide and neither of them contain fluorine. So oxygen in each case here is going to be -2. Our next rule for a specific nonmetal is for the halogens. The halogens are -1 for fluorine always. And that's really the only one that you need to remember. The rest reads it's -1 for other halogens except when combined with oxygen or other halogens. I wouldn't worry about memorizing that. Just remember that without exception, fluorine is always -1. And then the last rule is very important, and it's going to help us many times. You'll see it says the sum of oxidation numbers for all atoms in a molecule or polyatomic ion equals the charge of the molecule or ion. So remember that molecules have an overall charge of 0. So if I'm going to look at this methane molecule here, I don't have a rule for carbon, so I'm just going to let that be X. And then I have 4 hydrogens that are -1, and that has to add up to the charge, which is 0. So I hope that you can see that X must be -4. So there we go, -4 for the carbon there. We only have one other outstanding oxidation number. It's for the carbon in CO2. And we're going to use rule number 4 again. We don't know the oxidation number of the carbon. We have 2 oxygens that each equal to -2. And that has to add up to the charge on our CO2 molecule, which is 0. So X -4 equals 0. So X must be +4. So there we go. So in that way, using these 4 rules, we were able to assign oxidation numbers to everything in our equation. And what you'll observe is that some oxidation numbers stay the same and some increase while others decrease. So perhaps you can see that the carbon here increased its oxidation number by 8, and the oxygen here in every case ends up decreasing its oxidation number by -2. So by observing these increases and decreases, we're going to be able to deduce the number of electrons that were transferred and how they were transferred between our reactants. So the first thing that you'd want to do is just practice assigning oxidation numbers. I'll do a couple here, and you might find it helpful to pause the video and give a few a go by yourself. So I'm going to do the second column here. So sodium in this compound is present as a monatomic ion. So sodium's going to have oxidation number +1. This compound is not hydrogen peroxide, and there's no fluorine present, so oxygen is going to be -2. So that just leaves chlorine, and we're going to use rule number 4 to figure out what chlorine is. So the overall charge on this compound is 0, and we have +1 for the sodium. We don't know what the chlorine is, so we're just going to let that be X. And then we've got 4 lots of -2 for the oxygens. And all of that has to add up to 0. So what we have is X -7 equals 0. So X must be 7. So the sodium is +1, the oxygen is -2, and the chlorine is +7. In our next compound, we're going to use one that I said that you may not need to worry about remembering, and that is that the halogens are -1, except for when fluorine is present. So chlorine is going to be -1 here. guess I lied to you about not really needing that rule. And then the phosphorus we're going to have to figure out using rule 4. So x plus 5 lots of minus 1 adds up to 0. So x must be plus 5. There we go. And so on and so forth. Phosphorus, we don't have a specific rule for phosphorus. We'll come back to it. But oxygen is minus 2 in this case because there's no fluorine and it's not hydrogen peroxide. So let's do our little bit of math here. We've got 2 phosphoruses, and when they're combined with our 5 oxygens, it has to add up to 0. So 2x minus 10 equals 0. And I hope you agree with me that x must be plus 5. And there we go. And so on and so forth. We have barium here, and we have chlorine here. This is an ionic compound, and so what that means is that the charge on these monatomic ions is equal to the oxidation number. So barium always forms a +2 ion, and chlorine always forms a -1 ion, so not a lot of work there. Here we have oxygen and fluorine. We have a very hard rule there that says fluorine is always -1. So then if we want to get what oxygen is, we can use rule 4. So x for the oxygen, 2 times -1 for the fluorine, has to equal 0. So x must be +2. So oxygen is +2. So you get real quick at doing some simple algebra, and you can use a calculator if you need be. Just take your time, make sure you get the correct oxidation numbers. So why is this useful? Well, oxidation can now be defined as an increase in oxidation number, and reduction can now be defined as a decrease in oxidation number. So going back to our simple example, we knew just through observation that the magnesium was becoming oxidized, or was being oxidized, but now we can see that if we track through oxidation numbers. Magnesium as an element has an oxidation number of 0. Magnesium as a monatomic ion has an oxidation number of +2. You can see that the oxidation numbers increased, so therefore we would say the magnesium underwent oxidation. Similarly for the oxygen, elemental oxygen has an oxidation number of 0. As a monatomic ion, the oxidation number is just equal to the charge. In this case, the oxidation number went down from 0 to -2, and a decrease in oxidation number is what we're going to define as being reduction. So this is really helpful for those non-obvious cases. We just look at what reactant had an atom where the oxidation number increased. That reactant underwent oxidation. And then we look for a reactant where there was an atom that had a decrease in oxidation number. That reactant underwent reduction. So let's have a look at our example here. We assign oxidation numbers to every atom, and I hope you can see that the carbon in the methane changed oxidation number from -4 to +4, so that indicates that the methane was oxidized. Similarly, if we look at our other reactant, we see that the oxygen, the 4 oxygen atoms, their oxidation number changed from 0 to -2, so that reactant underwent reduction. So that's pretty cool. So we know, because oxidation is loss and reduction is gain, that the electrons are moving from the methane to the oxygen. Okay. Just reiterating, the reactant that is oxidized is described as being the reducing agent. And the reactant that is reduced is described as being the oxidizing reactant. And even though we might write half equations, it's important to realize that oxidation and reduction don't occur individually, they occur simultaneously, and the electrons move from one reactant to another due to the presence of the second reactant. That's why we say that the reactant that is oxidized is the reducing agent, as it causes the other reactant to be reduced. And similarly, the reactant that is reduced is called the oxidizing agent because it causes the other reactant to be oxidized. So you will need to identify not only what reactant is reduced or oxidized using oxidation numbers, but you also should be familiar with the terms reducing agent and oxidizing agent and be able to assign what reactant is the reducing agent and what reactant is the oxidizing agent. Now, another interesting quality of the oxidation number is that the change in oxidation number indicates the number of electrons that are being transferred. So if we look at the example that we've been working with, we can see that our carbon, our one carbon atom, changes its oxidation number from -4 to +4. So the increase in oxidation number indicates that the reactant containing the carbon was oxidized. The change in the value of the oxidation number was 8. So that means that our methane molecule is losing 8 electrons. Now, where do those 8 electrons go? Well, they get transferred to our other reactant. So now, not only are we able to identify what reactant the electrons are moving from to, we can also identify how many electrons are being transferred. Now, this makes sense because if the methane is giving up 8 electrons, then we have these 4 oxygen atoms here, and each of these 4 oxygen atoms change their oxidation number by 2. So 4 times 2 equals 8 electrons being gained, and so that makes sense, right? So 8 electrons are being transferred from the one methane to the 2 oxygen molecules. Okay. In that case, it was relatively easy to figure out how many electrons were being transferred because we only had the one carbon atom. But in the following example, we have more than one of every atom type present. So that's going to kind of complicate things a little bit. So let's go ahead and assign everything oxidation numbers. So if you begin with the oxygen, that's an element. So it's going to have oxidation number 0. And then we have hydrogen, and that's not with a metal, it's with a non-metal, which means it's going to have oxidation number +1. And then how I would figure out the oxidation number of the N in the N2H4 is by using our rule that the oxidation numbers have to sum to the charge on the species, which in this case is going to be 0. So 2x plus 4 has to equal 0. So that means that x must be -2. Okay, we take a similar approach with the products. N2 is an element, so it has oxidation number of 0. Hydrogen here is present with a non-metal, not with a metal, so it has oxidation number of +1. And then oxygen in this compound, it's not hydrogen peroxide and there's no fluorine present, so the oxygen must have oxidation number of -2. A more difficult problem now is to figure out the number of electrons that were transferred between the reactants. So, if we consider oxidation numbers, we can see that the nitrogen in N2H4 increase their oxidation number from -2 to 0. So that means that they underwent oxidation. Similarly, we can look at the oxygen atoms in O2 and we see that they decreased their oxidation number from 0 to -2 and underwent reduction. Now, we have two nitrogen atoms that change their oxidation number by 2. So that means, well, 2 times 2, that 4 electrons were lost by those nitrogen atoms. Similarly, we have 2 oxygen atoms that change their oxidation number by 2, and so that indicates that 2 electrons were gained by each of those oxygen atoms, giving a total of 4 electrons being gained. So in reality, what happened was that 4 electrons were transferred from our N2H4 molecule to our O2 molecule. So a total of 4 electrons get transferred because each of the 2 nitrogen atoms changes their oxidation number by 2, and each of the 2 oxygen atoms also change their oxidation number by 2. So now we're going to look at another example of a redox reaction where it's not quite obvious what's going on. So it says the reaction of silver plus aqueous ions with solid copper results in the formation of solid silver and copper 2 plus aqueous ions. So it would be tempting to kind of write the net ionic equation for this reaction as follows. 1 silver ion reacts with 1 copper solid to produce 1 solid silver and 1 copper 2 plus ion. And it is correct that this reaction is balanced for each of the atom types that are present. So in both the reactants and the products, we have 1 silver and we have 1 copper. However, if you're observant, you'll see that along the way, we gained a positive charge, which means that an electron got destroyed. This equation doesn't balance for charge. We have to do something to make it balance for charge because we can't just have electrons disappearing and appearing out of nothingness. So to balance redox reactions, we need to account for the fact that the electrons are being transferred among the reactants. So if we assign oxidation numbers here, we kind of get a better picture of what's going on. The silver ion has an oxidation number of +1, whereas elemental silver will have an oxidation number of 0. Elemental copper has an oxidation number of 0, but copper 2 plus ions will have an oxidation number of +2. So the change in oxidation number of the silver indicates that 1 electron is being gained, whereas the change in oxidation number of the copper indicates that 2 electrons are being lost. And so you can see the problem with our equation here. More electrons are being lost than are being gained, and we have to account for that extra electron. So when we want to balance redox reactions, we're going to use a multi-step process. Sometimes this can be as many as 8 steps. This one is particularly simple and doesn't require all 8 steps. We'll go through the 8 steps right at the very end. Regardless of the scenario, the very first step will always be to write a half equation for each of your reactants. So in our system, we have copper becoming copper 2 plus, and our other reactant, silver ions, becoming silver. Now we've identified these as oxidation and reduction. Sometimes that's not possible. Don't worry about identifying it as oxidation and reduction. Just write the half reactions, one for each reactant. Our next step is to balance each half equation for mass. Now, when I look at these half equations in this case, it's really simple because each half equation is already balanced. In my first half equation, I have 1 copper on each side, and in my second one, I have 1 silver on each side. So in this case, particularly easy, there's nothing to do. Once we've got everything balanced for mass, we're now going to balance for charge by adding electrons. So if I look at the left-hand side of my first half reaction, I have no charge there. But before I balance by adding electrons, I will see that I have a total +2 charge. So to get this down to 0, I'm going to add 2 electrons in, and now I have the same charge on both sides. So there I'm adding in 2 electrons. My second half equation, I began, before I added in any electrons, with a +1 on the left and a 0 on the right. So I have to get +1 down to 0. So for that reason, I add in 1 negative to get me to 0. So note that the electrons are always added to the more positive side. So identify the total charge on either side of your arrow, and then add enough electrons to the positive side so that they are both equal, so that the charge is equal on both sides of the arrow. So that's really it. We're good now. So we've got now 2 balanced half equations. What we need to do now is multiply each half equation by whole numbers so that electrons lost equals electrons gained. So in my first half equation, I had 1 electron being lost, and in my second half equation, I had 1 electron being gained. So what I'm going to have to do is multiply my second half reaction by 2. So everything gets multiplied by 2, so that electrons lost equals electrons gained. And then once I get to this point, what I'm going to do now is I'm going to add these 2 half equations together. And when I add them together, I'm going to cancel out things that appear on opposite sides of the arrow. So we're going to add together, and at the very least, the electrons will cancel out. So in this case, the electrons cancel out, and here is my overall balanced equation. What I want to do at this point is check that everything balances, including not just the atom types, but also the charges. So on the left, I have 1 copper, 2 silvers, and a total of +2 charge. And on the right, I have 1 copper, 2 silvers, and a total of +2 charge. So everything looks good, and I successfully balanced my redox equation. So let's have a look at another one. Here's my unbalanced redox equation. The first thing I'm going to do is break it into half equations, 1 for each reactant. So that's what I've done there. Having done that, what I'm going to do is I'm going to balance for mass. So I have 1 tin on either side of my arrow in my first reaction, but in my second reaction I have 2 iodines on the left and only 1 on the right. So I'm going to balance for mass by putting a 2 in front of my I minus. Now I have to balance for charge, and to do that I'm going to add electrons to the more positive side of each equation. So we've got a +2 charge on the left for my first one, and a +4 on my right, on the right for my second one. So I'm going to add in 2 electrons to the more positive side. In my second equation, I have no charge on the left, and I have -2 on the right. So I'm going to add in 2 electrons to get that to balance. So now we're balanced for both mass and charge. Our next step is to multiply one or both of our equations by a whole number to make sure that electrons lost equals electrons gained. And in this case, there's nothing to do because 2 electrons are being lost in our first equation and 2 electrons are being gained in our second equation. So we can just go ahead and add these guys together. So when we add together, we're going to cancel out what we can, things that appear on opposite sides of the arrow, and then that gives us our overall equation. And so all we need to do now is a double check to make sure that both the number of atom types is the same on each side of the arrow, and also that the total charge adds up to the same on either side of the arrow. So when we do that, we find that everything looks good and our redox equation is balanced. Things can become more complicated though, in particular the balancing for mass. If a redox reaction is occurring in acidic solution, we have to modify our procedure slightly to take into account the presence of H+. So here we have an unbalanced redox reaction, and it's indicated that the reaction is taking place in acidic conditions. We're going to follow the same step for same process for step 1, but for step 2, we're going to modify our balancing for mass procedure slightly. So we can see here that the iron is being oxidized from a 2+ oxidation state to a 3+ oxidation state. Furthermore, we can see that the manganese is being reduced from the +7 oxidation state to the +2 oxidation state. So we're going to break this into oxidation and reduction equations, one for the iron and one for the permanganate ion, MnO4-. And I should point out, you don't need to identify what is being oxidized and reduced before breaking your reaction into half equations. This is just kind of like I'm just doing it for the fun of it. So we're going to write our half equations, one for each reactant, and here they are. And that's no different from what we've been doing before. Now it comes time to balance for mass. And what's going to be different this time is we're going to take into account our acidic conditions. So the first step in balancing for mass when we have acidic conditions, in fact for any conditions, you can just do this every time, is to balance for every atom except oxygen and hydrogen. And that's particularly easy in this case because in our first reaction we have one iron on both the left and the right of the arrow, and we have one manganese on both the left and the right of the arrow. Now we're going to balance for oxygen, and how we balance for oxygen is by adding water. Our first half equation doesn't have any oxygen in it, so nothing to do there. But our second half equation has 4 oxygens on the left, so for that reason, we're going to add 4 waters to the right. Now, there's only one problem. By adding water, not only do we add a bunch of oxygens, which we want, we also add a bunch of hydrogen atoms, which we haven't accounted for. So we better go ahead and rectify the hydrogen atoms that we just brought out of balance. And how we're going to balance for hydrogen is we're going to add H+. And we can get away with this because we're working in acidic conditions. So to balance out the 4 waters that I added, we're going to have to add 8 hydrogen ions, to the left-hand side of our second equation. Okay, now there's a slight problem. It's kind of like the little old lady that swallowed a spider to swallow a fly. By adding H+, we add in a bunch of positive charge, and that's going to mess our charges up. So we're going to have to use electrons now to fix up our positive charge. So our final step in balancing for mass is to balance for charge by adding electrons. So in our first equation, before we added any electrons, we had +2 on the left, +3 on the right. So we always add electrons to our more positive side. So we're going to add in 1 electron to get that to balance. In our second equation, before we balanced for charge, we had a total charge of 7+ on the left and a total charge of 2+ on the right. So we're always going to add electrons to the more positive side. So to get 7 down to 2, we're going to need to add in 5 electrons. Okay, so now we've got the charge and the mass all balanced out. We can go ahead and push our equations together. But first we're going to have to multiply one or both of our equations to make sure that electrons lost equals electrons gained. And I hope you can see what needs to happen. We're going to have to multiply our top one by 5 to make sure that we have 5 electrons being lost, because we need 5 electrons being gained in our second equation. So we multiply everything in our first equation by 5, and there we are. So it looks like at this point we're good to go ahead and add things together. So what we're going to do now, add our two half reactions together, cancelling where we can. At the very least, the electrons should disappear. So we're going to add our two half equations together. Our electrons will cancel. In this case, there's nothing else that can cancel. So here's our overall balanced equation in aqueous acidic conditions. When we go through and check everything, we'll find that every atom type balances, and also we balance for the overall charge. So here we are, we go through and check everything. 5 ions on the left, 5 ions on the right, 8 hydrogens on the left, 8 hydrogens on the right, 1 manganese on the left, 1 on the right, 4 oxygens on the left, 4 oxygens on the right, and an overall charge of 17 on both sides. If a redox reaction is occurring in basic solution, we're going to follow the same procedure as for an acidic solution, but once we have our overall balanced equation, we'll do one additional final step to switch on over to basic conditions. So we'll illustrate this with the following example. So here we have the unbalanced redox reaction between manganese 2+ ions and oxygen to generate MnO2, which is an ionic compound, and we're told that this reaction is occurring under basic conditions. So let's just assign some oxidation numbers to things to see what's going on. The manganese 2+ ion, because it's a monatomic ion, has an oxidation number of +2, and then the manganese in MnO2 must have an oxidation number of 4+ to offset the 2 oxygens, which each have an oxidation number of -2. So in conclusion, the manganese 2+ ions are oxidized by 2 electrons from the +2 state to the +4 state. The oxygen in its elemental form has an oxidation number of 0, but in the manganese MnO2 in the ionic compound, it will have an oxidation number of -2 because it's going to be in the ionic form. So the oxygen is reduced by 2 electrons for each oxygen. Okay, so let's break this into two half reactions now. We have one representing the oxidation of Mn2+ to MnO2, and then for the oxygen, which is the reduction, I haven't written a product because we can just balance oxygen out with water in a moment. So now we have the system broken into two half reactions. What we're going to do now is balance for atoms other than oxygen and hydrogen, which is the manganese, and you can see that that's already balanced. So we've balanced for everything other than oxygen and hydrogen, which means we're not going to do anything. And then we're going to balance for oxygen with water. So in our first equation, we have 2 oxygens on the right, so we're going to need 2 waters on the left. And in our second equation, we have 2 oxygens on the left, so we're going to need 2 waters on the right. So adding those in, it's going to look like so. Okay, so now we've balanced for oxygen, we're going to have to balance for hydrogen. And looking at this, what do we see? Well, we have 4 hydrogens on the left in our first equation, so we're going to need 4 H pluses on the right to balance those guys out. And then in our second equation, we have 4 hydrogens on the right, so we're going to need 4 H plus on the left to balance them out. So putting that in, this is what it looks like. So at this point, we're ready to go ahead and balance for charge. In our first equation, I hope you can see that we have a +2 charge on the left, but a +4 charge on the right. So we would add in 2 electrons to get that to balance to the right-hand side. And then in our second equation, we have a +4 charge on the left and a 0 charge on the right. So that's going to take 4 electrons to balance that out. So we can go ahead and add in those electrons, and that's going to look like this. Now, once we get to this point, we realize that in our oxidation, we are losing 2 electrons, but in our reduction, we are gaining 4. So we're going to have to multiply our oxidation half reaction by 2 in order to generate the 4 electrons that we need for the second step. So I'm going to go ahead and multiply everything in my first half reaction by a factor of 2. So doing that gets me to here. So at this point, the number of electrons lost equals the number of electrons gained, and I can go ahead and add my 2 half reactions together, cancelling my electrons and anything else that might happen to cancel. And in this case, it looks like I'm going to be able to cancel out some of the water and some of the hydrogen ions. So there we go, all of the electrons cancel, 2 of the waters cancel, leaving 2 remaining in my oxidation half reaction, and 4 of the hydrogens cancel, leaving 4 hydrogen ions remaining in my oxidation half reaction. So we put all of that together, making sure we write everything down without skipping anything, and we end up with this equation here, which is perfectly balanced if we were in acidic conditions. However, we're in basic conditions, which is where our extra step comes in, and so now we have to switch on over to basic conditions. And what we've got to do this is we're going to add 1 OH minus to both sides for every hydrogen ion that is present. So for each hydrogen ion present, you are going to add 1 hydroxide ion to each side of the equation. So we had 4 hydrogens present, so we're going to add 4 hydroxides to each side. Now, hydroxides combine with hydrogen ions to form water. So we're going to go ahead and do that. We're going to combine these guys together to make 4 waters. Okay? But then we can see, hopefully you can then see that 2 of those waters are going to cancel out, leaving only 2 remaining on the product side. So my overall balanced equation looks like what I got in the box here. 4 hydroxide ions plus 2 manganese 2+ ions react with O2 to form 2 manganese 4 oxides and 2 water molecules. And that's my balanced equation in basic solution. And if I go through and check all of my atom types and check the overall total charge, you'll see that everything balances in the way that it's meant to. So let's just summarize everything. This is the list of rules that are in your book for balancing half reactions using this method. So we're going to write the 2 half reactions representing the redox process, 1 for each reactant. We'll balance all of the elements except for oxygen and hydrogen. And then we'll balance for oxygen by adding water molecules. Once we have the oxygen balanced, we're then going to balance for hydrogen atoms by adding H+ ions. Having balanced the H+ ions, we're then going to balance the charge by adding electrons to the more positive side. At this point, you should have 1 equation where electrons are being lost and 1 equation where electrons are being gained. That is, the electrons should be on opposite sides of the half reactions. If needed, multiply each half reaction's coefficient by the smallest possible whole number to yield equal number of electrons in both equations. Then you're going to add your half reactions together and simplify by removing things that appear on both sides of the arrow in the same form. Once we've done that, we will be balanced if we are in acidic conditions or neutral conditions. However, if we are in basic conditions, we'll need to do a few more steps. The first of which is we're going to add 1 hydroxide ion to both sides of our equation for every H+ ion that is present. Then we're going to combine H+ and OH- ions to form water molecules. And then if we have any water molecules that can cancel, we're going to go ahead and cancel those water molecules. And then once everything's all wrapped up, you want to make sure that your equation balances for both the number of atoms present and also the total charge present. So having done that, you'll have your balanced redox equation. So let's have a look at a problem from the OpenStax book. And what we're doing here is we are balancing half reactions. So let's look at the first one. This looks like it's a reduction because the tin is beginning with oxidation number +4 and it is ending with oxidation number +2. So in order to balance this guy, the atoms other than oxygen and hydrogen are balanced. Oxygen and hydrogen themselves are balanced. We just need to balance for charge. We have +4 charge on the left, +2 charge on the right. So we're going to add in 2 electrons because we always add electrons to the more positive side. And now the total charge on both sides is +2 and everything is balanced. In the second example, we have this quite complicated cation, and it reacts to form Ag and NH3. So what has happened here? Well, we need to balance for atoms that are not oxygen and hydrogen. So silver is balanced. We have 1 on either side. Nitrogen is not balanced. We have 2 on the left, but we have only 1 on the right. So I'm going to need 2 nitrogens over there. And now they are balanced. Okay, so now we're going to balance for oxygens by adding waters. There are no oxygens, so oxygen is balanced. And then finally, I'm going to balance for hydrogen by adding H+. So on the left, I have 2 times 3, that's 6 H pluses. And on the right, I have 2 times 3, that is also 6 H pluses. So hydrogens are balanced. Only one last thing to balance, which is charge. And on the left, I have a charge of +1. On the right, I have a charge of 0. So always add electrons to the more positive side. I'm going to put an electron there. And so that looks like everything is now balanced. And we can check our answers against what OpenStax has. And that looks good. And that looks good as well. So that concludes the video on the third type of reaction that we're discussing in section 4.2, oxidation reduction reactions.